learners, welcome to Education Online program. So in our previous lesson, I've been looking at the applications of heat transfer by convection, where we looked at the land breeze and the sea breeze, where we say that it occurs due to the difference in the air pressure, and the difference in the air pressure, which is also caused by the difference in their specific heat capacity. So we also looked at with the radiations, where we talked about the polished and the dull surfaces, which one is actually the good heat emitter and the heat absorber. So we are going to continue with the applications of the forms of heat transfer. So today we shall be looking at the thermos, which is sometimes known as the vacuum flask. The thermos, or we can call it the vacuum flask. So what is actually this flask? How does it work? So if we're talking about a vacuum flask, we're talking about a device. This device keeps cold water cold, or any liquid that is in it cold, or it can keep it hot. It depends on what you've kept in it. If it was hot, it has to keep the liquid hot, but then if it is cold, it will continue keeping it cold, not changing it from hot to cold, and then maybe from cold to hot. How does this look like? Let's have a very simple diagram of this thermos. So the thermos is made out of silvered surfaces. It also has a cork. It has the vacuum seal. On top of it, it also have a vacuum inside it. Let us look at the diagram here. This is a very simple one. We shall have our first silvered surface here. This is our next silver surface. So we say there were two silvered surfaces. This would be our first surface. So what is in between the first silver surface and the second silvered surface? It is the vacuum. So that means that in our diagram we have to create space for the vacuum. So we shall a vacuum means an empty space, a space that is not occupied with anything. So we shall try to create a vacuum right here. Let's have that. Okay, this is our next silvered surface. So what is it having again? We said it has a vacuum seal, so we need a provision for the vacuum seal. What else are we lacking? We already have our vacuum. We have the silvered surfaces. We have the vacuum seal. We don't have the cork. Where is the cork supposed to be? Here, which is for covering the top part. That is our cork. So which one is actually, where are the two silver surfaces we're talking about? This one and this other inside one here. So these are the silvered surfaces. So which one is our vacuum? We have this space between the two silvered surface becomes our vacuum. So we also wanted a vacuum seal. Where is the vacuum seal? This one right here is our vacuum. Vacuum seal. So we have the cork. The cork is what we use on top here to cover the flask. So that's our cork. So what is lacking there? We have the anti-soak pad. The anti-soak pad is this one here, these two. So we have, I can just have this side here as a anti-soak pad. So that is our simple diagram of a thermos, or what is known as the vacuum flask. So if we say that a vacuum flask is supposed to keep hot water hot or cold water cold, don't you think that there are supposed to be some heat transfer? Because if you look at a vacuum, it has liquid inside, and we said with liquid there is this convection form of heat transfer that will happen in there when there is molecule of this liquid, even the gases. And then we see that there is solid surfaces here, which is supposed to have the transfer of heat between them using the conduction process. So what kind of heat losses can we have here? You see that when you keep your liquid here, sometimes you come and find that liquid is already cold for the case of hot liquid. Or if you had it warm, you find it has cooled already. Why? It cools because there is exchange of heat with the liquid in the flask, and then the surrounding environment. Since we say that the air pressure between the two cannot be the same, so that kind of heat exchange causes it to lose heat from the liquid. So when it loses the heat, that heat is being gained by the surrounding. So let us look at these heat losses. We have it as heat. In a vacuum, flask. So what are these heat losses? The heat losses will be, it can be by conduction. The heat loss can be by convection, or it can also be by radiation. So these are the forms of heat losses that occur in a vacuum flask that makes it not to keep its liquid hot, or the cold one to remain as cold as it was. Because of this, what do you think causes this? Why do we incur this kind of heat losses in that? So you will see that we have contact. There is contact between the materials or the system, and there is also a vacuum there. So you see that these heat losses can be minimized. They can be minimized in a way that if you put your liquid there in the flask, it will take it some time for it to cool, or it will take it some time for it to warm for the case of cold liquid. So how can we minimize this heat loss in a vacuum flask? So let us see How to minimize? In a vacuum flask. So for us to minimize these heat losses, we already have the construction. The way the flask is designed, it is designed to avoid this heat loss. So if you look at conduction and convection, these two can be minimized in a flask easily. How can this heat transfer be minimized there? If you look at our flask, it has what is known as the cork. Because in a conduction and convection form of heat transfer, they need a material medium. Because if there is no material medium, there will be no form of heat transfer. But then here we already had the material, we had it, the liquid is there. So if we want it not to release this heat to the surrounding, we have the cork. So this cork here, it is mostly made out of wood. So wood is a very bad conductor of heat. That means that the wood does not allow heat to flow through it that easily. So if it does not allow that, it means that for the liquid to lose its heat to lose its energy by conduction or convection process, it is going to block it. Then the currents here will not move out of the flask. So in the flask we can say that the conduction and convection can be minimized by use of the cork. So it is not only the cork that can minimize that heat loss there. We said it needs a material medium. But if you come and check our flask here, our flask has got a vacuum. The first silvered surface, it is more like two containers brought together. There is the first container, then there is space, and then the second container. You see that the first container does not actually touch the second container there. So that vacuum there minimizes heat loss by also conduction and convection. So because if there is no material medium there, with conduction it needs a direct contact. If there is no direct contact between the two systems, that means that there is no form of heat loss that will occur from the first silvered surface to the second. So we shall say conduction can be minimized by the presence of the vacuum. We've been talking about conduction only and the convection. What of radiation? Is there no heat transfer that can occur here by radiation? There would be loss of heat from this liquid by radiation. But then how can we minimize it also? To minimize the effect of radiation, you see that these two containers here have been polished. They have not been polished dark or black, but they are polished with silver. So that surface inside there has got silver coating. Why is it having that silver coating? That is now to reduce the effects of heat loss by radiation. Because we say that silvered surfaces are very bad emitters of heat. So we can have we can reduce it. The radiation can be minimized by using silvered surfaces. So you see that the design alone of the vacuum flask allows us to reduce this kind of effects. So the liquid that is kept in it will always remain the same way. But then there is a situation where when you keep your liquid there, it will still cool after a long period. Why? Because however much you try to minimize this heat loss, there will still be escape of the energy. So the longer the liquid is going to stay in the vacuum flask, that means that there will be the heat loss still. So that is why you find out that after 2 days or 3 days, you see that the liquid you've kept, the hot liquid you kept in the flask is already cold, because there is still some little, a very little to very little degree that this heat transfers occur. So with this we come to the end of the applications of heat transfer. So we're going to look at something very interesting, which is the thermal expansion of matter. Let's look at the thermal expansion of matter. From the word expansion, we have expansion, we have the matter, and we have another word which is the thermal. Thermal there can be representing our heat, and then we have the expansion. What does it mean? For expansion, it means for something to increase in size. So what of the matter? We know matter is anything that occupies space. You see that? So if you're talking of thermal expansion of matter, we are meaning the effect of heat on the matter. So you find out that when there is any object, you try to heat the object up, what happens? The object will increase in size. So when it increases in size, what is the effect? That's what we are going to look at. So when you're talking about the thermal expansion of matter, we're saying this is the increase in size of an object when heated. So how does something increase in size when you've heated it? We say that matter comprises of tiny particles. So you see that when you heat the object, these tiny particles are going to be loosened. And when they are loosened, that means they can move from one place to another. Loosening it meaning that they are going to you're weakening their bond. So if the bond is weakened between them, instead of them contracting and coming together, they will instead be moving away from each other. So that movement away from one molecule or one electron to another will cause the object to expand. So let us look at the expansion of solids. Expansion of solids. How do solids expand? Let us take an example of a let's take an example of a let me say a metal ball. So we're going to have a metal ball. This is our metal ball. We're going to try this. We're going to try to fix it in a have a ring. Then the ring is to measure how big the metal ball is. So you see that when you have our metal ball there, we have our ring. When you try it in this ring, this is a ring. So this is a cold metal ball. When it is still cold, try to fix it in the ring. You'll see that this metal ball will fit in the ring. Get a ring that is proportional to that metal ball. Make sure that it is not the ring is not bigger than the ball, or the ball is not bigger than the ring, but they should be proportional. You just fit and it like fits totally in the ring. So after you seeing that the metal fits in the ring, you now remove your ball and heat it up. So after heating it for some time, you get your ball and try to fix it in the ring here. So this one was cold. This time you've heated it because here you were heating it. This is the heat. So after heating it, we are getting it here and again to put it in to fix it in the metal, into the ring. Let's see what will happen. This is our ring. Make it a bit proportional there. I want it to be the same size as the first one. There. Here we are still using the same ring. Remember, it is the same. It's the same metal ball we're using here, so it should be the same ring. So now, after heating your ball, try to bring it and fix it in the ring again. You'll see that it will not fit in the ring. It is going to be bigger than the ring. Instead of this point coming direct inside, it will be left out. Why? Because there was expansion during the heating. The molecules were the bond between the electrons of this particle here has been weakened. So instead of them now coming together to contract, they are moving away from each other. So that movement alone from each other, they are trying to create space for each other. So when you're trying to force to create the space, you see that the metal ball actually expands. So when you try to fix it there, what happens? It will not fix. It will not fit, because now they are not proportional. This one also happens at home when you have these metallic doors. During hot weather, try to close this door. You'll see what will happen. Sometimes you'll find the door, you'll try to pull the door actually closes very well. But then at times when you come, we try to close your door. You will need to use a lot of force to pull the door. Sometimes it totally refuses. Why? Because there was expansion. Because if you've not created a gap for the expansion of this, that's why you see that there is a difficulty in closing and opening this door when it has expanded. And that mostly happens during what? During hot weather. Because during hot weather, you're increasing the kinetic energy of this material, the particles in the material. So they will need to move, and their bond is broken. So you see that the object, that door is going to increase in size. So that is the reason why when you sometimes come to the door, it fails to close. Sometimes it can close, so easily. So we also have another example of this, which is known as the bimetallic strip. So when we talk about the bimetallic strip, what do we mean? We have the bimetallic strip. This is all to check the expansion of matter, the thermal expansion. So with metallic, you can also check the effect with bimetallic strip, where you have to combine two materials together. These materials should not be of the same. They shouldn't be the same actually, because if you like using a copper, you can use a copper and iron, or you can use a brass and iron. Those are made out of different materials. So what happens with this? You see that different metals expand at different rates. Even though you equally heat them, they will still expand at different rates. So you see that when you get a bimetallic strip, you have your this time we are making a copper. Let's take a combination of copper. We are combining, we want to tie them together. So we shall have this one having the copper, and this one down is our iron. So we want to tie these two together. So when you tie them like this is just the rope. So this is our copper. Let's try to make it a bit different. And then this is our iron. So we are going to take this bimetallic strip and heat it. The concept behind here is we are tying it together like that to see whether it is true that the two materials actually expand at different rate. However much you apply the same amount of heat. So you see that when you tie them together, try to heat. So when you see that before heating, they are fitting together. We've taken the same length. The length of the copper is the same with the length of the iron, and also their width. They both have got the same width. What we want to see is that whether it is true they expand differently. So you see that when you now heat this, instead of your metallic strip to look like that, it is going to change its shape to something like this. We have it like that, and then this. We had our ropes, they were tied. So you see that this one here on top is still the copper rod. This one is the copper rod, and then this is the iron rod. So look at the shape after heating. This is after, and this was before heating. Look at the two shapes. There was a change in the shape. We expected them to expand similarly, but then they ended up giving us this shape. This is because copper has a higher rate of expansion than the iron. So you see that the one that expands actually faster is going to have a very bigger, or we can say a wider curve than that's the one that expands least. That's why you see that the copper, instead of this expanding this way, so that we can have we shall have our copper here, and then the one after it will be the iron, you get that curve, meaning that this one expanded faster and increased in its size than the iron. So this is how you can find how the rate at which your materials actually expand. You can not only using copper and the iron, you can also try with steel and the iron. You can also use brass. So you can try all those experiments at your free time at home. So today this is what we've seen. We started with the thermal flask, where we said it's a device that keeps hot liquid hot and cold liquid cold. We looked at the heat losses in the thermal flask, where we said there are three forms. That is the conduction, convection, and radiation form of heat loss. We also looked at how to minimize the heat losses, where we said we can use the cork to minimize the heat loss by conduction and convection, and we can also use the vacuum. We create the vacuum to minimize the heat loss by conduction, and then the heat loss by radiation is being minimized by painting the flask with a silver paint, because we said it is a bad emitter of heat. So we came and looked at the thermal expansion of matter, where we said it's just the increase in the size of an object when it is heated. So we're also saying that every object expands at a different rate from the other. So because of to see the effect of that, we use the bimetallic strip, which is the example of copper and iron. So we saw that copper expanded actually faster than the iron. That's why there is a change in the shape of our in the shape of our bimetallic strip there. So with this, we come to the end of our lesson. We shall meet again in the next lesson.